Okay, guys, so today I will be discussing Aldol reactions. And just to review, Aldol reactions are typically introduced your second semester of organic chemistry. And these reactions are specific to aldehydes and ketones. Originally, when it was first discovered between two aldehydes. And it was this two-step reaction where step one required an aldehyde, and I'll call this aldehyde 1. You treat your aldehyde with a base, and just like we've seen in our previous two lectures, you deprotonate at the alpha position to form your conjugate base. So nothing new. Just like before, you can draw resonance structures to this. And just like before, there are two possible resonance structures. You have your Z-enolate, and you have your E-enolate. Now, we don't really talk about this in second semester organic chemistry. We just talk about the formation of an enolate period, right? Now we're actually differentiating between our alkenes, which is what we did in our previous lectures. And so we've discussed on how you label these enolates. And step one is deprotonation of your alpha carbon to form your E-enolate, which, of course, as you learned before, is your nucleophile. Okay. Step two requires that you take your enolate, i.e. your conjugate base. And so I'm going to draw it as my conjugate base. And the only reason I'm drawing it as my conjugate base is because I don't want to redraw the Z in the E enolate right now. I'll do that eventually. I'm just trying to provide you with a really general reaction and mechanism. But I'll get to a few more details. Now, in step two, you treat it with an electrophile. In the previous last two lectures, we used our alkyl halide as our electrophile. Now we're going to use a second carbonyl compound or an aldehyde, a second aldehyde, and I'll label it different. We've got our electrophilic center, which is our carbonyl carbon. And that's where the nucleophile attacks. We've got our negative charge on our oxygen. And then finally, we treat it with a proton source, whether that proton source is water or acid. And we protonate our oxygen. So really the only difference between this and the previous two lectures is that our electrophile has changed. Okay, now we've got a carbonyl electrophile. And so if you remember, the carbon right next door to the carbonyl is alpha, and then next to that is our beta carbon. The Aldol reaction proceeds to always give us a beta hydroxy carbonyl compound, i.e. the alcohol group must always be at the beta position. not gamma, not delta, not alpha, but beta. If your hydroxy group is not at the beta position, beta relative to the carbonyl, of course, then it's wrong. Okay. And that really does help with the connectivity if you don't want to number your carbons. And so this reaction was known as the Aldol reaction because originally it was between two aldehydes to provide an alcohol. Now they've extended the scope of this reaction where you no longer need two aldehydes. And this reaction can be also between two ketones. It can also be between an aldehyde and a ketone, where the aldehyde's the nucleophile and the ketone's the electrophile, or it can be between a ketone nucleophile and an aldehyde electrophile. Regardless of what the carbonyl compound is, aldehyde or ketone, you will always get a beta hydroxy carbonyl compound. There's no ands or buts about it. Okay. And so what I'm going to do is I'm going to redraw this product down here and give myself a little bit more space. Because now I want to discuss the specifics of the mechanism and of the product. Okay. So let me again label alpha, beta. So this is my final product. Now, here's the thing. In Chem 124, we just tell you aldehyde, ketone, beta hydroxycarbonyl compound. We don't talk about Z-enolate. We don't talk about E-enolate. And we definitely do not talk about the fact that you are forming two stereocenters. We really do teach you the very basics in organic chemistry. And so what we're trying to focus on in this case is the fact that, hey, you are forming two stereocenters, which means that this really is a mixture of four products, making this reaction incredibly inefficient. Okay. And so let me go ahead and draw out those four products. Product number one includes the formation of the syn product. Now, in this case, the two substituents are wedged, but you can also have them dashed. So these are my syn products. Okay, let me move it to the center. Not only do you have the syn products, but it shouldn't come as a surprise that you'll also have the anti-products. You will have two anti-products. And there are my two anti-products. So these are the four products that you will always observe from your Aldol reaction, right? But the overall goal is to make one out of the four. I don't want all four products. Overall goal is to only make one out of the four. Okay. And so to make one out of the four, we need to figure out how all of these four molecules are related to each other. And we'll start off pretty simple. these are enantiomers of each other. According to the definition of enantiomers, all stereocenters have inversion of stereochemistry. So you can see that all the carbon stereocenters have completely inverted between the two. And not surprisingly, the same is true in this case. These are enantiomers. Okay. Now we have to worry about diastereomers. And diastereomers are specific to anything with more than one stereocenter. Again, make sure you review your definitions. Diastereomers is anything with more than one stereocenter. Okay? Now we have to start grouping those as well. Additionally, diastereocenters is defined by at least one of the stereocenters in your molecule not changing. So I'm going to label these in different color. These are diastereomers of each other. Note that the carbon bearing the alcohol groups is the only stereocenter that hasn't changed. Let's go ahead and finish up the remaining and grouping the remaining diastereomers. This and this molecule are diastereomers with the carbon groups bearing the R1 substituent remains the same. Diastereomers. Might get a little crowded. These two are diastereomers where the carbon bearing the R1 groups remained the same. And then finally, the end molecules. In these cases, it's the carbon bearing the alcohol groups that remained the same. These are diastereomers of each other. And so we're done, right? We've labeled all of our enantiomers. We've labeled all of our diastereomers. Okay. And so what we want to do is we want to form one enantiomer out of the 4 enantiomers. And so we're just redefining our task. And what this lecture will do is we will figure out how to make one enantiomer over the other 3. Okay? But we're going to start off slowly. And we are going to focus on only making 2 out of the 4. Okay? And work our way to 1. Okay. And so there are a couple of rules when it comes to this. And so the first step of our reaction was to deprotonate, right? And I told you that you will either form the Z-enolate or the E-enolate. And so let me go ahead and draw those 2 out. Oh, excuse me. This is E-enolate. I'll go ahead and highlight these. Okay. And what you'll see is that the Z-enolate in the presence of your electrophile And I'll draw the electrophiles for both. Possible reactions. The Z-enolate in the presence of your electrophile will always give you the syn products. And let me draw out both syn products. Whether your substituents are wedged or whether your substituents are dashed. So here are my syn products. And you will get these products in a 1-to-1 ratio, i.e. a racemic mixture. Okay. Your E-enolate is going to give you, not surprisingly, your anti-products. And I'll draw out both anti-products. And it's going to give you, the E-enolate is going to give you the anti-products in a 1-to-1 ratio as well, also racemic mixture. Okay. And so it's your enolate that dictates what products you are going to get. Okay. The take-home message: enolate geometry dictates products formed. Okay. Let me draw out a line between these, because I do want to say a little bit more when it comes to this. These are diastereomers of these. Okay. And vice versa. These are diastereomers of these groups. Okay. And so the reaction that we're first learning is a diastereoselective reaction, where you're forming two products, but you're forming the diastereomers of the other two products. Okay. This is a diastereoselective reaction. You're forming two products over the other two diastereomers. Okay. Okay. So what we have to worry about is, how do I force my reaction to only form the Z-enolate? And how do I form my reaction to only form the E-enolate? Okay. The metal, i.e. Lewis acid, used dictates the enolate that is formed. Okay. So your Lewis acid, this just means Lewis acid, used for the reaction, dictates what enolate you are going to form. And typically, the Lewis acid you use is a boron Lewis acid. Now, in Chem 124, you don't introduce a Lewis acid. All you do is you introduce a base. Okay? But now we are introducing a Lewis acid. And why are we doing that? Why introduce a Lewis acid. Let's talk about the general reaction. And we'll focus on step 1 first. Okay. Forming my enolate. Now, typically you want a Lewis acid and a boron Lewis acid. Ooh, that boron looks terrible. So that when you donate your electrons from your carbonyl oxygen to the Lewis acid, you activate your carbonyl group. And what I mean by activating your carbonyl group, you've got your dipole, making these protons more acidic and easy to deprotonate by a base. Okay. Don't forget that OTF is a triflate and it looks as follows. It's a good leaving group. We typically use it as a leaving group in Chem 24, Chem 124. Okay. And so once it activates, it kicks off the triflate. I apologize, I didn't show that at the very beginning. I've activated my carbonyl group. And once I've activated my carbonyl group, I make these alpha protons more acidic and it can introduce my base. I deprotonate. To neutralize that positive charge on my oxygen. Okay. And I can form either my Z-enolate or my E-enolate, just like I mentioned before. So let me go ahead and draw out my Z-enolate first. And I'll draw out my E-enolate. Okay. Before I move on, your base is typically triethylamine or diisopropyl ethylamine, diisopropyl ethylamine, also known as dipea. Diisopropyl ethylamine. Really popular amine base. Typically, people just say, I'm using dipea, and everyone knows that it's diisopropyl ethylamine. Okay. So the Lewis acid is used to activate that carbonyl and make my alpha hydrogens much more acidic. Reason number 1. Reason number 2 is that once it deprotonates, my boron stays complexed to my oxygen. And that's incredibly necessary, okay? Because once your boron is complex to your oxygen, it can dictate what enolate you're going to form. So why is that? It all depends on the R group on the boron. Okay, let me highlight this. When you have an R group that is large, it will favor the formation of your E-enolate, which should make sense because if you have a large R group, then you have, excuse me, and you have an Z-enolate, then the R1 and the R group on the boron are crowding each other, i.e. sterics. The Z-enolate is not favored. And so if you have a large R group and you have the E-enolate, note that your hydrogen atom is the smallest atom on the periodic table, and there is little to no crowding. And your E-enolate is favored. Okay? So when your R group on the boron is large, it favors the E-enolate. Okay? One of the most popular groups on boron for the formation of the E-enolate, popular boron Lewis acid for formation of E-enolate is when you have cyclohexyl groups. On your boron. Which makes sense, right? Because these cyclohexyl groups, the way I've drawn them right now, look like they're on the plane of the board, but they're not, right? They're chair conformations that are flipping, okay? And so these are bulky, large groups. And because of this, let me redraw it. When you use this Lewis acid, they're the same thing. I'm just drawing it as a no triflate. When you use it, this will always favor the formation of your E-enolate, always. This can also be drawn out or thought of as cyclohexyl groups. CY for cyclohexyl. You don't want to draw out the cyclohexyl groups, the 6 carbons. You can just draw out CY for cyclohexyl group. Okay. That's probably the most popular Lewis acid for the formation of the E-enolate. Okay. Now, it shouldn't come as a surprise that when you use small R groups, it will favor the Z-enolate. Okay. So let me draw out the Z-enolate. If you use really small R groups, it's pretty easy to favor the Z-enolate because there's very little steric hindrance. Now, this doesn't mean that you don't form the E-enolate, right? You probably do form the E-enolate, and there's very little of the E-enolate, but the majority of it favors the Z-enolates. And so some of the more popular R groups, popular boron, Lewis acids that favor formation of the Z-enolate are small methyl groups on my boron, surprisingly, phenyl groups on my boron. Well, Dr. Lucero, how can you have phenyl groups? Remember, double bonds between carbons are much smaller than single bonds between carbons, and the structure is a lot more rigid, right? Benzene rings aren't flipping chair conformations, they're just flat. So surprisingly, they're sometimes thought of as alkyl groups because they're so small. They're so rigid and they are pretty compact as opposed to cyclohexyl groups. And so they're thought of as small groups. You can also have butyl groups. One of the more surprising ones that students use and that we use in our lab a lot is 9-BBN. And this is what 9-BBN looks like. 9-BBN is a 9-membered ring where the boron is part of the 9-membered ring. And so it looks like two cyclohexyl groups joined together, but the boron is taking part of the formation of those rings, of those cyclohexyl groups. And because they're fused ring systems or bridged systems, it's a 9-membered ring, and it's thought of as 9-BBN. And it's one of the more popular boron reagents. This is not two cyclohexyl groups on boron. Boron is actually taking part in the formation of the cyclohexyl groups to form a bridged 9-membered ring system. Okay? So again, notice how boron is part of the structure. It's not two cyclohexyl groups on boron. It's boron making up the groups. Okay? So again, because it's actually part of the group, it's a lot smaller than two cyclohexyl groups on boron. Okay? So the way we're going to start this off is explaining why the Z-enolate gives syn products only. And then we'll move on as to why the E-enolate gives anti-products only. And so in order to understand the Z-enolate and why it's only given us syn products, we must look at the transition state of the reaction. Okay. And you have to make sure that you can see things three-dimensionally because we are going to be looking at a transition state. That is a six-membered chair conformation. Also known as the Zimmerman-Traxler transition state. You need to learn how to draw these six-membered chair conformations or these Zimmerman-Traxler transition states, which means that you need to learn how to flip chairs and draw axial and equatorial substituents as well. Okay. So what I'm going to do is I'm going to try to draw it as slowly and color code things to make sure that you can see where the connectivity is occurring. But again, you need to see things three-dimensionally. So please make sure that if you can't see it, you come see me because we're drawing six-membered rings. So again, we're going to start off with our Z-enolate. And what I'll do is I'll draw my enolate in red. And I'll draw my carbonyl compound, i.e. my electrophile, in what looks like blue or purple. Okay. So completely different. This is my nucleophile. This is my electrophile. Okay. Because each enolate gives us two different products, we will draw the transition state to both products. Okay. Again, each enolate gives us two different products. We will draw the transition state to each product. Remember, there is no chirality in our starting materials. Okay. Our enolate, i.e. our nucleophile, is flat. Okay. Because it is flat, my electrophile can approach the enolate from the front or from the back. Okay. Again, electrophile can approach from front or from the back. That's really important to note. And so we will draw the transition states from the electrophile approaching the front and the electrophile approaching the back. So let's first talk about the electrophile approaching the front of enolate. Now, in order to do this, because it approaches it and it's a six-membered ring transition state or the Zimmerman-Traxler transition state, we need to redraw our enolate. And so we rotate it around a little bit. So what do I mean by that? Okay. And this is what I mean. I'm just going to rotate it about 90 degrees. Okay. And it's going to look as follows. So not only have I rotated it, I've also drawn out the bonds from the R group to the boron. Okay. But you can still see that it is my Z enolate. The oxygen and the R1 group are on the same face. Okay. The hydrogens are cis to each other. All I've done is rotated and drawn out the bonds between my R's and my boron. That's it. That's all I've done. And I'm going to do it again. So same thing. And I'm just redrawing it to sort of prove a point. All I did was just rotate it. Okay. So they look exactly the same. Nothing has changed. It's a flat molecule because it's an alkene, right? Alkenes are flat. And now my aldehyde is going to approach from the front. I'm just worried about the front right now. Okay. Electrophile approaching front of my enolate. Now, the reason I drew my enolate twice is because my electrophile, my carbonyl, can approach the front in two very different directions. What do you mean by that? When it is approaching, it can approach as follows. And let me draw this in blue. Or at least I think it's blue. Also a flat molecule, right? This is one of the ways it can approach, or it can approach as follows. Okay. Now, a couple of things that I wanted you to see as I'm drawing this. The way I'm moving things around, the reason I'm moving things around is because my transition state is a six-membered ring. I know I keep repeating myself, but I want to make sure you understand that because I want my transition state to look like a six-membered ring. So what do I mean? If you draw what's happening, my carbonyl oxygen is complexing to my boron. It's my alpha carbon that has to complex to my carbonyl. And I have to generate my double bond so that you can kind of see how they're approaching each other and forming a six-membered ring. Okay? The same thing in this figure as well. The carbonyl oxygen of my aldehyde is complexing to my boron. Once it complexes, it can regenerate the double bond. And the alpha carbon should be the carbon that attacks my carbonyl to give electrons to my oxygen. And so you can start seeing the six-membered ring and the Zimmerman-Traxler transition state. Transition states. Now here's the thing. One transition state is favored over the other. Which transition state is favored? And why? We'll call this transition state A and transition state B. Okay. The one that is favored is transition state A. Why? You have to remember chair conformations. Okay. And in chair conformations, structure B has what's known as 1,3 diaxial interactions. Okay. If you remember from your chair conformations, I'm going to draw a chair here. Substituents prefer to be in the equatorial position over the axial position. Oh, excuse me. Because in the axial position, there are 1,3 diaxial interactions. Please make sure you review that. 1,3 diaxial interactions. The numbering has nothing to do with naming the molecule. The numbering has to do between the positioning of the axial substituents. You can start here, and you'll notice that at carbon 3, there's an axial hydrogen. You can start here and notice that on the other side, if I go left, I've got a substituent in the axial. So it's just 1,3 diaxial interactions. You can also, excuse me, you don't necessarily need to start numbering at the carbon I started numbering. If you start here with 1, again, at carbon 3, there's an axial substituent. If I start numbering on the other side, at carbon 3, there's an axial hydrogen. These are known as 1,3 diaxial interactions that aren't favored. And so if we look at our system structure B, we can see that the alkyl group is in the axial position and will therefore cause 1,3 diaxial interactions in the Zimmerman-Traxler transition state. However, if the aldehyde has the hydrogen, the 1,3 diaxial interactions aren't bad. It's just a small hydrogen as opposed to a large alkyl group. Do you guys see that? So the aldehyde can approach the enolate from the front, and it can approach it from the front with the hydrogen in the axial position or with the R group in the axial position. And if you have to choose, you will always choose the hydrogen in the axial position. Okay? And so this is no longer, draw it in green. a valid transition state. This is the transition state we move forward with. Okay. Okay, so there's my Z-enolate aldehyde approaching from the front. This is just the aldehyde approaching from the front. We will talk about the aldehyde approaching from the back. Let me just finish this up. Now that I've got this Z-enolate, I can start forming and breaking bonds. But as I'm forming and breaking bonds, I am going to keep it in six-membered ring form. When I was taking the class, it was easier for me to keep it in six-membered ring form so that I could see everything three-dimensionally. So what do I mean by that? And I'll try to draw it down here as best as I possibly can. I'll continue to color code if that's easier. I now have a carbonyl. Because notice this bond broke. So now I've got a carbonyl. Let me draw that a little straight, or as straight as I possibly can. Please notice nothing has changed here. It still looks the same. Now I've got a single bond instead of a double bond. So I've drawn out my single bond. I'm drawing it slowly so that you can follow. Now I've got a new bond to my carbonyl, and I'll draw this in blue. My hydrogen is facing up. I've got a single bond. And my new substituent is in the equatorial position. And you can see the new bond between the oxygen and the boron that I created. Do you see that? Notice that it still looks like a six-membered ring. Okay. Then, of course, I add water or a proton source, which can be an acid. And I protonate my oxygen. And again, I'll do the same thing. I'll color code everything for you so that you can see where everything is coming from. Now it's protonated. Okay. So I'm done. This is my six-membered ring, or the product resulting from my Zimmerman transition state. But Dr. Lucero, how is this the syn product? Or how is this one of the syn products? How is this one of the syn products? And this is where you have to see things three-dimensionally. And I usually tell students the best way to see it for me was to, this is a three-dimensional structure. Notice that in six-membered rings, you never draw wedges, you never draw dashes. It's already a chair conformation. It is already wedged and dashed when you're drawing it in chair conformation. It's already three-dimensional. It's when you unwind it and put it into two-dimensional context that you have to start drawing it three-dimensionally. And so right now, this is all three-dimensional. And what I typically tell the students, well, this is part of my 6-membered ring. So I just look at this is my eye. I just look down at it. I just want to look down at it. And once I start looking down at it, as opposed to looking at it from the side, now I can start drawing it two-dimensionally with wedges and dashes. So let me number. 1, 2, 3. Those are the 3 carbons that I care about. The only 3, excuse me. So when I draw it, I'm going to draw it in red. I'm going to draw my carbonyl first. That's 1. It's flat, so I don't have to worry about the stereochemistry. Okay, it's going down, so I'll draw carbon 2 going down. It's then going up, so I'll draw carbon 3 going up. Label it 3. It's going down. I'll label the rest. But now I need to add stereochemistry to 2 and 3. So what do? Please notice that at carbon 2, the hydrogen is coming out towards you. It's literally poking me in the eye. So at carbon 2, I will need to draw the hydrogen coming out. I'm going to draw this in red, towards me. And if the hydrogen is coming out towards me and poking me in the eye, that means that my R1 group is dash. Okay. I'll go on to carbon 3, which is facing up. Notice that the hydrogen is also on the same face as the hydrogen at carbon 2 that's coming out towards me, which means that it is also wedged. Notice that the alcohol group is away from me, so it must be dashed. Do you guys see that? And so if you notice, you have the syn conformation. And this specific transition state, where the aldehyde comes in from the front, is actually giving me the OH and the R1 group syn and dashed. Okay, this is only explaining one of the syn products. It is not explaining the syn wedged. It is just explaining the syn dashed product. Okay. So the Z-enolate with the aldehyde approaching the front gives us the syn dashed. So now we can talk about the electrophile approaching the back of the enolate. Electrophile approaching the back of the Z-enolate. And so it shouldn't come as a surprise that the electrophile approaching the back of the Z-enolate should give us the syn wedged product, but we'll draw it again. And I'll do the same thing I did before. I'll draw out my enolate first, specifically my Z-enolate. Now, because we've already explained that the aldehyde has to approach with the hydrogen in the axial position, I'll just draw one Z-enolate. I won't do it twice again because I know that's a lot. So now it's approaching, my carbonyl compound is approaching the back. These Traxler transition states were probably the hardest for me when my aldehyde was approaching the back, so bear with me, because again, I'm trying to position everything where you can see the six-membered transition state. So my aldehyde is approaching the back. And it's complexing to my boron. And you can see where my six-membered ring is forming, hopefully. Okay. Please notice that as it's approaching the back, or as it's approaching from the back, it's the hydrogen that's axial. Just like before, exactly like before. This is a double bond. That's right behind my hydrogen. And I did that specifically to show you that the hydrogen is up front and the double bond is in the back. Okay. Just like before, I'm going to start forming the bonds. I'll try to stay consistent with the coloring so that you can see the things that are forming. Double bond now. And in the back, I've got my boron bonded to my oxygen. Just like before, exactly like before. Again, because it's going through a six-membered bearing transition state, you can't draw wedges, you can't draw dashes until you convert it into a two-dimensional structure, which is what we'll do. And because I wanted to stay consistent with the way I was doing things when I was taking this class, I would look at this molecule again from the top. That's how I look at my molecule. If you can see it naturally, by all means, but seeing things three-dimensionally can be pretty scary. I'll do the exact same things that I did before. I'll number these. 1, 2, 3. Please notice that now the numbering is from right to left, as opposed from left to right, which is what it was before. Okay? Okay. So just like before, I like to start off with my carbonyl, which is what I number always as 1. So this is the same thing as, but again, my carbonyl group is now on the right. Oh, let me color code this. There's carbon 1. Then go down, and it's carbon 2. Then go up, and it's carbon 3. And then, of course, the rest of my group. Oh. Okay. Now I have to worry about the substituents at carbons 2 and carbon 3. Okay. Let's start with my carbon 2. Please notice, again, the hydrogen is coming out towards me. So it is wedged, which means that my R1 group is dashed. I then look at carbon 3, and the hydrogen is on the same phase as my hydrogen on carbon 2. You can see that my oxygen is facing away from me. And so I have got my oxygen away. I didn't protonate in this case because I'm trying to get to help you understand where my stereochemistry is going to, which means that my hydrogen is wedged. Okay. Now I'll go ahead and protonate. I should have protonated, but that's okay. You can protonate with water or acid. Regardless, it still gives us the same stereochemistry. But Dr. Lucero, this is also got my hydroxyl group and my R1 group dashed. Well, no, because my aldehyde in this case is on the right side. And if I flip it around so that my aldehyde is now on the left side, now my R1 group is wedged. And my OH group is wedged. And so now I have formed the syn and wedged product from the aldehyde coming in from the back. Do you guys see that? The beauty of organic chemistry is that it's three-dimensional, but that's also the downfall of falling out of love with organic chemistry, because you do have to rotate and flip things around and see things three-dimensionally. And even though you're looking at a cyclohexyl transition state or a six-membered ring transition state, you need to make sure that you can see it from different directions, whether it's the side, the top, the bottom. And once you can see it, it makes things so much easier. Okay, you guys, so this is just the syn dashed and the syn wedged products. You get both products. In the next lecture video, I'll go ahead and talk about the anti. And we're just focusing on forming two products over one. Okay?